Hi, linear algebra students. So we are in video number 3 of cross product and triple product. Okay, so in this video, I'm going to do two things. First, I'm going to present the triple product and all the theorems that are related to it. It's actually a very, very simple thing for one big reason, and the reason is right here. We're going to talk about it. And the second thing that I will do, sorry about that, I was spacing out, is that we will start talking about the application of both products. Okay, and the first one is being areas and volume. So we will present it, and then we will do one example. The example in the example, we will find the area of a triangle. You will see that. Okay, so first of all, you have three vectors in our tree: u, v, and w. So their triple product is a number, first of all. So it's not a vector. This time around, it's a number. And it's obtained very simply by doing the dot product of u with the cross of v and w. Okay, so you take the cross product, u cross w, and what you get is a vector. And then with that vector, you do the dot product with u. So that's the triple product. Okay, and so you know how the dot product and the cross product looks like. But the nice thing about putting them all together is that you end up with the determinant of the three vectors when you put them as columns. Okay, the proof is in the supplements playlist. It is optional. You don't have to watch it. But know that if you're doing a scalar triple product, the only thing you really need to do is to put the three vectors in a determinant and you calculate the determinant. That's it. Okay? By the way, it's with this formula that the cross product was invented. Okay? So now let's go ahead with the corollary. Okay, so now that we know that the triple product is the determinant of u, v, w, it makes it clear that the cross product is orthogonal to both u and v. Okay, because what happens if you put these three vectors in a determinant? Okay, well, you got the determinant of u, v. Okay, but you know that this determinant is 0 because the columns are linearly dependent. And the same thing happens if you do this, right? If you do like v, u, v, okay? So the determinant is also 0 because in both cases, like that's it, the columns are LD. So actually, I should say here, since the columns are LD, because that's how you get that the determinant is 0. Since the columns are linearly dependent. Okay. Honestly, that's all you need to know about the triple product. Okay, but we will see very soon the applications it has. So that's why you need to be prepared to calculate it. Now, did I write any property with it? No. Okay, it's not worth writing its property, honestly. So applications of cross product and triple product. The first one is to find areas and volumes. Okay, so suppose you have vectors in our tree. Okay, so this is interesting. Okay, the fact that it's in our tree. Why? It's because you already saw that if you have vectors in R2, the area of the parallelogram is going to be the determinant of the vectors. But this won't be true in R3, okay? Because in R3, we have an extra dimension. So the area of the parallelogram, let's put a little bit of color here. So the area of the parallelogram determined by u and v is u is the norm of u cross v, okay? And the volume of the parallelepiped determined by u, v, and w is the triple product. Okay, this totally makes sense because you already know that the volume of the parallelepiped is the determinant with these three vectors. So the second part makes real sense. The first part, I will just mention that, okay, let's erase everything here, okay? except maybe the title. Okay, so let's just mention here that the proof of number 1, so proof of 1 is in the supplements playlist. Okay, it is this time around mandatory. Okay, so you do have to watch it. So it's mandatory. So once you finish watching the video number 3, so this video, it would actually be a good idea to watch this supplement as well. Okay, so just to make sure that you don't spread yourself around. Okay. All right, and it uses the fact, so if you want to actually try it yourself, it uses the formula that we saw in the previous video, the fact that the norm of u cross v is the norm of u multiplied by the norm of v times the sine of theta. Okay, so it uses that formula. All right, so example. We want to find the area of a triangle in our tree. So we are given 3 points. So given A, which will be equal to 3, 0, 1. B, which will be the point 1, 1, 1. 1, 1, 1. And C will be the point, so let's say 2, -3, 1. So the problem is to find the area of the triangle ABC. So find area of triangle ABC. Okay. Now, before we solve the problem, let's just set it up. Okay, so we have, okay, we don't really care, by the way, about the exact location of ABC in space. So let's say they're like this. Okay, suppose. Okay, and this is our triangle. You want to find the area of. Okay. So, all right, the idea is actually quite simple. So you will define a vector. You will take it, let's say, from A to B. Okay, so like this, let's call this the vector. Yeah, call it the vector u. And then we will define a vector from A to C. And what do we get out of this? Well, the area of the parallelogram, so this area right here, okay, will be the norm of u cross v. Okay, so this is like, this will be the norm of u cross v. Okay, however, the triangle actually stops here. Okay, so this is where the triangle stops. That being said, it's easy to justify that the area we are looking for is half, right? So actually, let's not draw the line yet, but let's actually resketch this thing over here. So A, B, C. So yeah, you have like B, A, and C. Okay. So the arrow, and again, right, you have the vector V over here and the vector U over here. Sorry about that. Well, it's really not hard to justify that the area that we're actually looking for is 1/2 of the area of that's it, like the dot product between U and V. The cross product, what am I saying? Sorry about that, guys. So here you go, cross product of U and V. So with that in mind, let's get going. The only thing we need to do is to engineer the ingredients. So, all right, what is the vector U? Well, the vector U is going to be A and b, right? So b minus a. So in other words, what do we have? We have 3 minus 1, 2. 0 minus 1. Wait. Okay, I see what's happening here. Let's actually write both points. Okay, otherwise I might confuse myself. So b minus a, you write both of them, and then you get finally the vector u, which is negative 2, 1, 0. Ingredient number 1. Now ingredient number 2, you want to engineer the vector v. So the vector v is c minus a. Now c is this guy right here, and a we're taking the same. So we're going to have 2, negative 3, 1, minus, again, the vector 3, 0, 1. So that's going to give us negative 1, negative 3, and 0. All right, I need to erase the setup like the application in order to continue. But as you can see, we're nearly done. We need to calculate the cross product. Okay? So actually, let's not calculate the norm yet. Let's calculate the cross product directly. So U cross V. All right. So now I remind you, my favorite way of calculating it is just by setting up the components, right? So don't forget, we have 3 determinants. Okay? And don't forget also that the one in the middle is bearing a negative sign, right? So, all right, now we have to be careful. We're using, for the first determinant, we are using, do I have enough color? Black, yeah, black, blue, and orange. That's perfect. So for the first determinant, we're using the second and the third. So in other words, we're having here 1, 0, and negative 3, 0. For the second determinant, so I will use orange this time around, you're using the first and the third. So in other words, you have negative 2, 0, negative 1. I'm puzzled here. No, it's okay. Negative 2, 0, and negative 1, 0. Yeah, that works. Okay, perfect. And now, to get the, what color did I say again? I said blue. Perfect. So for the third determinant, you're using the first and the second. Okay? So you will have negative 2, 1, and negative 1, negative 3. Okay? Now you calculate each of the determinants. So what are you going to get? Okay, so let's actually write it in vector notation. So you're going to get 0 for the first component. You're going to get 0 for the second component as well. And then for the third component, you're going to get 6 plus 1, so 7. All right. Now, the only thing you have left to do is to apply this formula, right? So the area, is equal to 1/2 of the norm of the cross product. Well, in this case, we're lucky because what do we have? Well, we have here the square root of, let's actually write it as a square root, but as you can see, it's actually way simpler than that. So it's going to be the square root of all 3 components squared, like with signs. So let's actually keep the color code just in order not to get confused. So then plus. And what turns out is that you have the square root of 7 squared, so it's going to give just 7, right? So the final answer is simply going to be 7 over 2. If you want to write unit squared, you're certainly allowed, but otherwise, this is the final answer. Hopefully this was good. So in the next video, we're gonna see the second application. Actually, we're gonna see the two last applications, which is to find the normal vector of a plane, but also to verify if two lines are skew or not. I will give detail. See you there.